So yesterday we talked about evaluating limits graphically is essentially what we did yesterday, right? We talked about when a limit doesn't exist, and we looked at a bunch of graphs, all right? Now, we don't want to have to think about graphs every single time we want to evaluate a limit, okay? So we're going to talk over the next few days, which will be next week, right? We're going to talk about evaluating limits just based on their equation, which we call analytically. Okay. So here are a few basic rules for the beginning of our analytic process. Okay. So we'll talk about the first one. If we have the limit as x approaches c of just a value, like 5, 7, 2.1, b is just a number, then the limit is that number. Actually, you know what? Just write those three down and then I'll talk about them so that way we don't get. Okay, so basically this is the limit of a constant. What does the constant function look like? What kind of line? It's going to be a horizontal line. Okay? No matter what limit I ask you to find here, what y value is it always going to be approaching? Right? Whatever b is. Okay? So if you have a constant, the limit toward whatever number it is going to be that constant. Okay? That's what that one is saying. Okay? Number 2, the limit as x approaches c of x is just c. All right? We know this is the identity function. Okay? Whatever the x value is, the y value is. Okay? So we can essentially just plug that c value in. Okay? Same thing here. The limit as x approaches c of x to a power is just c to that power. Okay? It's basically giving you the y value of that function. Right? Because that's what we would be approaching. Okay? So we're going to talk about a couple examples here. Okay, you know what? Let's talk about them one at a time. Okay, so first example, the limit as x approaches 2 of 5. Following the rules that we just wrote down, Bruin, what would that limit be? Look up here. 5 is just a constant, right? So we're talking about this rule right here.
Oh, so 5.
Yep. If it's just a constant, the limit is that constant. Okay. Next example, the limit as x approaches 2 of x. Michael, if you look up at these rules, what would this limit be? 2. Okay? X approaches 2 of x is 2. All right, and then the last one, the limit as x approaches 2 of x cubed. Okay, according to those basic rules, this limit would be what, Eli? 2 cubed, very good. So we could say that that limit is 8. Okay, so we have a basic start here. I'm going to go through some limit properties. You could write these down or you could reference them in your book, okay? I don't want to take a large chunk of time to write them down because there are more important things that we need to write down here pretty soon. And so if you want to write them down, that's fine. Or you can just say, you know, this is 1.2, theorem 1.2 in the book. Okay, if you want to look in your book at them. All right. So basically what happens if we have 2 different limits? Okay. Both of these limits are of x approaches c. They're of 2 different functions and they have 2 different values. Okay, so we have the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is k. Okay, we're going to talk about the different properties of combining these 2 limits together. All right. The first one is a scalar multiple. If we have a scalar multiple of our function, then that limit will also have the scalar multiple. This is on page 59, if you want to reference it there. If you are going to combine the 2 functions by addition or subtraction, then you can combine the 2 limits by that same operation. Multiplication is the same way. If we have a product of the 2 functions, then we can take the product of their limits. Same with the quotient. We just know that we cannot divide by 0. And then the last one is that if we take our function to a power, then that limit can also be taken to a power. Okay, so we'll use these properties throughout the unit. You might not actually think of the property when you use it, but you'll see these properties throughout. Okay. So over here we talked about basic limits. Okay. Well, what happens when we get into equations that are big polynomials, or they're rationals, or they have radicals, or whatever? We need to have kind of a system for how we evaluate limits, okay? So the very first thing I'm always going to tell you to do is what's called direct substitution, and that's what we're going to work on here for the next 10 minutes, okay? Direct substitution. Okay, as long as we have, and really, I'm going to have you try this. It says you can only do it with rational functions that have non-zero denominators. I'm going to have you try direct substitution, and if you get a 0 in the denominator, then we know we have to use something else, okay? But we're always going to try direct substitution first. It's going to be kind of the first thing off of our checklist when we are analytically solving a limit. Okay? Direct substitution, all it means is you're plugging in the value to the function for your limit. Okay? Now, like I was talking about earlier, some of this first unit in calculus and even the second unit, we're really getting used to some new notation, okay? I don't really like today's notes because there's a lot of writing, but we just have to get used to the notation, okay? So we're going to write a couple of things down, and then we're going to do examples that don't take us very long, okay? But we have to get used to the notation, okay? So let's say we have a polynomial. Okay, if we have a polynomial, the limit as x approaches c of the polynomial, to evaluate it, we just plug in c to the polynomial to get our limit. That is what that means. Since x is approaching c, we plug c into the function to get ourselves a value. That's the limit. Same thing for a rational function. Okay, we're going to plug that value in. We just don't want that denominator to be 0. Okay. Essentially, you're plugging that c value in for x and getting a y value. Okay. We know that if our function is, like if there's not a hole in our function, okay, let me give you a graphical example here. Okay. Here is the graph y equals x squared. Here's the coordinate 2, 4. We know graphically as we approach x equals 2, we're approaching that y coordinate of 4. Okay? All we're doing is finding basically the y value of that x coordinate. That's what we're doing with direct substitution. We know that if we follow the curve, we're going to approach that coordinate. Okay? So we're going to do a couple examples. Like I said, the examples are going to take less time than writing down the rules. That's okay. Go ahead and write this one down. The limit as x approaches 3 of 3x plus x squared. Okay, so direct substitution means we're just plugging in this value right here into x. So the limit as x approaches 3 of 3x plus x squared is just 18. That's it. We wrote a lot of stuff down for like just that one little example, right? I know. But you'll appreciate the notation later. The limit as x approaches 3 of 2 over x cubed. Write it down. To evaluate this, we're just going to take 2 over, since we're approaching 3, we're plugging 3 in. So we have 2 over 27. We're done. That's done, right? Okay. The same thing is true for any radical functions. Okay, we can use direct substitution when we have a radical function, as long as it does not create, as long as the c value is in the domain of the function, right? Odd radicals, not a problem. Even radicals, we can't have negative numbers underneath. Okay. Okay, go ahead and do that example if you haven't done so already. And then check your answer with your neighbor when you have one. All right, Jenna, what did you get? 3 radical 3. If you leave it as radical 27, I'm not going to be upset or count you off points. Okay? So I would accept radical 27, and I would accept 3 radical 3. Why do I do that? The AP test does not require you to simplify for full credit on their pre-response questions, and so I'm going to do the same. However, if there were a multiple choice question, their answers will be simplified all the way. So we need to know how to do it, but it's not a requirement all the time. Okay. All right, so let's talk about situations where direct substitution isn't going to work. Okay? There are going to be times where we have a rational function and our denominator is 0. Okay? What do we do in that case? All right? There are some things that can happen. All right? So what I'd like you to do is copy down this limit right here. Words aren't coming to me very fast today. How many of you were at the game last night? most of you. Okay, so let's talk about what happens when we try to use direct substitution. When we plug in 2, what do we get in our numerator? What do we get in our denominator? Okay, that is not a value. Okay, however, what we can do is we can see if there is some algebra we can do to maybe simplify this equation so that we can use direct substitution. Okay, so what algebra technique might we suggest to help us? Okay, so let's write this as the limit as x approaches 2 of x minus 2 times x plus 2. Okay, that's helpful, right? Because what happens? Cancel out, and now we have the limit as x approaches 2 of x plus 2. Now can we use direct substitution? You betcha. What do we get? 4. Okay. All right. Analytically, we can see how this plays out. We factor, we cancel out some factors. We can use direct substitution. What is happening graphically? There is a hole. This is the line x plus 2 with a hole at x equals 2. So there is a line at x plus 2. There's a hole at the coordinate 2, 4. So as x approaches 2, our y values are approaching the hole at 4. Okay, so graphically, we know how to do it. Okay, here's how we do it analytically. We don't have to think about that graph every time. Thank God, right? You don't want to graph those all the time, do you? No. I know how some of you feel about rational functions and graphing them from last year. Right? Okay, now let's get a little bit even more excitement. Go ahead and write this one down. Okay. First, we always want to see if direct substitution will work. What do we get in the numerator with direct substitution? Denominator. That's not okay. We can't have something divided by 0, okay? If there's a 0 in the denominator, it's possible that the limit's not going to exist, but we need to see if there's anything algebraically we can do first. If you see 0 over 0, there's probably something algebraic that you can do, okay? What algebra can we do here? Would that keep or change the value of the function? It would change it, and we don't want to change, do we? Now, if we had an equation, Trevor, we could square both sides, right? But since we're just working with an expression, we have to be sure that we don't change the value of it. Okay, I like the idea, but let's keep brainstorming.
You could split it up into the square root of x plus 1 over x minus 1 over x. I don't know if we'll do anything.
Well, we would still have that 0 in the denominator, wouldn't we? Which is kind of what we're trying to avoid. So it's a good idea, but analytically we're still stuck with that 0 in the denominator. Okay?
Can you multiply by the reciprocal?
I'm gonna, can you explain what you mean by the reciprocal? I think you're on the right track, but I need to know what you think the reciprocal is.
We multiply it by x over 9x plus 1.
Okay. If we multiply by that, are we keeping or changing the value of the expression? Changing it. We don't want to do that. Okay, we do want to multiply by something though. That would be allowed to multiply. Whoops, you said x. We would be allowed to multiply top and bottom by x, but that would give us x squared in the denominator, which means we still are plugging in 0 to the denominator, right? We're getting closer. Okay, we need to multiply by a well-chosen 1, if you will. X over x isn't quite what we need. What about this? What's that called? The conjugate. Okay? We can take the conjugate of that strange little radical numerator. When we multiply, why would we multiply by the conjugate? What does that do for our numerator?
Cancels out.
It does cancel out something. Okay? Trevor, this is a minus b times a plus b. And we know that when we take a difference of squares, we get a squared minus b squared. So we cancel out the radical. Okay? Now, our denominator does not look fun, but we're going to get there. Okay? What happens in the numerator? It's just x. Oh, we have this x in the denominator that can cancel out. Okay. So now we are working with the limit as x approaches 0 of 1 over radical x plus 1 plus 1. Okay? You have to write the limit as x approaches 0 every time until you physically plug 0 in for x. Until you evaluate the limit, you still have to keep writing limit as x approaches blah, blah, blah. Limit as x approaches blah, blah, blah. Then when you plug it in, you can stop writing it. Let's plug in 0. What do we get? 1 over 2. Okay. There's a couple more things to talk about, but we don't get out of here until 9:45, and I'm going to remember that today. Okay. Go ahead and write this down. This is how we evaluate the limit of a composition. Okay. Now this is how the book describes the process. I'm going to show you another process that you can take as well. But essentially, just like you would evaluate a composition with functions, you want to plug values into the inside function and then plug them into the outside function. Another way of doing it is thinking of it as two limits. Like here, we're evaluating a limit and that number gets thrown into F, okay? If it's easier to think about, okay, we can evaluate the limit towards G, and then that gives us the limit that we need for F, okay? It's the same process, just taking a little bit different route, okay? On the next page, I have two functions. We're going to do a couple different limits with them. So I ask when I go to the next page, you write down those two functions so we can do a couple examples together. Okay. All right, we ready? And I know we're still figuring out all this notation. When we get into examples, okay, I'm hoping that the notation is going to get a little bit more comfortable. But go ahead and write down these two equations. Okay, the first one we're going to do is the limit as x approaches to of f of x divided by g of x. Okay, so this is kind of going back to the properties that we talked about way at the beginning. Okay, direct substitution. We're plugging 2 in for f, we're plugging 2 in for g. Okay, to evaluate the limit, we have f of 2 over g of 2. What is f of 2? 8. And what's g of 2? Square root of 2? Hey, you can leave it like that. Aren't you so excited about this? Okay. We're going to focus on the calculus, not the simplifying of numbers. Okay. All right, so what if I said the limit as x approaches to f of x times g of x? Okay. We're still just with direct substitution, plugging 2 into those two functions. Now we're going to multiply them together. Okay. You told me f of 2 was 8. You told me g of 2 was radical 2. So our limit is just 8 radical 2. All right. Now let's talk about the composition. Okay? The limit as x approaches 2 of f composed with g. Let's start with the inside function first. What is the limit as x approaches 2 of g of x? Radical 2. So what we're going to do is now we're going to take the limit as x approaches radical 2 of our outside function, f. So now when we plug radical 2 into f, what do we get? Okay. Do you remember when we were going over our quizzes yesterday? I think it was the fourth problem on it, the f of x plus 8 minus f of x over 8. And I said, this is really important. We're going to see this over and over. The time is coming. Okay. Now, instead of 8 up here, you see delta x. What does delta x mean? Change in x. okay? I am going to use delta x. For your algebra, if you wish to use h, I am not opposed to that. If you want to change delta x to h, you may. Just understand that you're going to see delta x, and then it means change of x. But I'm fine if you want to change it to h. Okay? So this is called the difference quotient. That's what you found on that fourth problem of your quiz. All right? And now we're taking the limit as delta x approaches 0, or like on your quiz as h would approach 0. Okay? We will talk about what this actually means in Unit 2, but we have to practice doing it. And since we're on our limits chapter, we're going to practice it here. So, we're going to pick an easy one. Just a nice linear 2x plus 1. So the limit of the difference quotient, we have the limit as delta x approaches 0 of f of x plus delta x. Okay, we plug x plus delta x into our function. We subtract the function all over delta x. Okay. Like I said, if you want to use h's, that is fine. Okay, so now let's, if we try to use direct substitution, we're going to get a 0 in the denominator. So every time you do the limit of the difference quotient, you have to simplify. All right? So we have the limit as delta x approaches 0. We distribute the 2 through, distribute the negative through, we get to here. What happens in our numerator? Everything cancels except 2 delta x, you say? Because we have 2x minus 2x, 1 minus 1. So we have 2 delta x over delta x. Our delta x's cancel. That should happen. By the time you get towards the end, that h or delta x should be able to cancel so that you can evaluate your limit. So now we have the limit as delta x approaches 0 of 2. What is that limit? Everybody together? With so much enthusiasm, I can't handle it. 2. Okay? All right. On your gold sheet, you will find the homework. I will put the gold sheet on my website so you can reference it. My calendar is also updated on my website. Okay? I know today was kind of boring. I promise it'll get more exciting. Okay? Please make sure you do your homework this weekend. I can't stress how important this assignment is right here. Okay? These skills are vital for the rest of the year. The year.